Welcome back to the discussion of spatial networks. In previous two videos, we primarily looked at the motivation, and we saw that spatial networks are societally very important. Many of us have already used them in navigation applications on our smartphone, as well as on web services like Google Maps. Right? What we want to do now is to go under the hood and see how these networks are modeled computationally, and then how do we design scalable algorithms so that we can compute spatial network queries like shortest path very quickly, even on road maps spanning the entire country or the whole world. Okay. So at the end of this module, we should be able to talk about conceptual models of spatial network. In a later video module, we'll come back and look at logical and physical model as well. And in particular, we are going to look at graph models. Okay, that is something which has nice mathematical properties and has been investigated in computer science for a long time, and it's a very popular computational model of spatial networks. Okay. So the big picture, essentially in this video and the next two videos, we are going to look at different models of spatial network. In this particular case, we are looking at conceptual model. So we'll look at conceptual model at two levels. One is the conceptual model from database perspective. It's often called the entity relationship diagram. And we saw a similar model in spatial query chapter describing the data sets involving country, river, and cities. In this chapter, we are going to describe road networks and spatial networks using this tool. But the main focus would be to understand the mathematical model called graph, because that's widely used both in mathematics and in software to model spatial networks. After this video, when we come back to next video, we'll look at logical data model, in some sense the facilities for querying it, as well as physical data model. How do we store networks so that we can scale up to very large networks? Okay. So without further ado, let's take a look at one of the spatial networks many of us are familiar with. Right? Probably most of us have used road maps in navigation application. So here we are showing a small picture of a tiny section of a road map near University of Minnesota in an area called Dinkytown. So you might actually recognize this cartography, very typical of Google Map. And here you see roads like 4th Street, which is sort of going from the right side to the left side, or 5th Street, which is going from left to the right, University Avenue, which is again going from east to west. But you also see these avenues, 5th Avenue and 6th Avenue. This is 5th and 6th, which are going sort of north-south direction. Now, if we were to model this using entity relationship diagram, then we often ask about the concepts which people use to think about road maps. So common concepts include the notion of roads, streets, and avenues, and we already illustrated many of those a few seconds ago. Okay. But in addition, people talk about road intersection. So for example, when you look at University Avenue and it intersects with 7th Avenue Southeast, this may be an intersection. Okay. So here is another intersection, okay, where 6th Avenue and 5th Street intersect. Okay. Another common concept is segment. Once we have the notion of road intersection, then people often decompose a road or a street into smaller pieces. So for example, if you look at this intersection and that intersection, then the segment of 5th Street, just this little piece that connects adjacent road intersection, is often thought of as a road segment. Okay. And so on. Okay. Another concept we will use is the notion of turns. And if you have driven in urban areas, you might have encountered many turn restrictions. It may say no left turn at this intersection if you're coming from north, or no right turn if you're coming from south, and so on. Some of these turn restrictions may be due to one-way nature of the road, right? And other may be imposed just to make the traffic flow smoothly, and so on. So there are many, many concepts we used when dealing with road maps, and all these concepts can be put together into an entity relationship diagram. So we'll quickly show you a very big picture, high level set of concepts that hopefully you have used before and many of us use in day-to-day life. So first concept is road map. You may look at a large paper map, or you may go to and look at a digital map. And this road map, as we just talked about, consists of many road intersections and many road segments. Okay. So in entity relationship diagram, when you see this chicken foot, it's saying a road map has many road intersections. And same way a road map has many road segments. Each road segment may have 2 road intersections that it connects. Okay. Other interesting concepts are those of the notion of the streets and roads themselves, which is being shown as a box here, and they can be modeled as a sequence of road segments. Okay. Turns may also be thought of as something imposed on a sequence of road segments. Okay. And same way routes, if you have your favorite route from home to work, again that's often modeled as a sequence of road segments and intersections. Okay. And, other ideas may be points of interest. On a road map, often certain places are highlighted, such as airports, right, or downtowns, schools, and these are often thought of as point of interest. They often have an address. In many countries, this address comes in the form of street address. So you may give the name of the street and then a building number on that particular street. But this is a new system. It's only about 100 to 150 years old, and countries like England and US have gone through a lot of legislative process to systematize it. But many other countries, we don't have street address, and there your address may be much more simpler. It may be based on a landmark, but if you have a smartphone and GPS, you can simply provide the latitude and longitude. So these addresses may come in many forms, okay, and so on. Another concept that we may visit later is the observational framework. Nowadays we have a lot of sensors on the road, and these sensors may be static or moving, and they observe different properties of the road and so on. And also in the map you need some kind of coordinate system. Latitude, longitude is one in order to specify these locations. So this is showing you a rich set of concepts people may use to model roads, and we have just given you a few common concepts, and you can probably enrich this diagram with more concepts. So let's now switch gears and look at the graph model. Okay. While entity relationship diagram was very rich, it could model many concepts, graph is a much simpler model. Okay. So let's first look at its mathematical definition and then apply it to model road maps. Okay. So mathematically, graph just is a pair. Okay. It has 2 components. A graph G has 2 components. The first symbol V stands for a set of nodes or vertices. Okay. The second symbol E stands for a set of edges, and they model one binary relationship among vertices. Okay. So let's illustrate it to see, if you were to use this to model road map, what would they look like? So here is the road map we saw before, which had many road intersections and many road segments connecting them. And one way to model it as a graph is to use road intersections as the nodes and road segments connecting adjacent intersections as the edges. And if you did that, the graph model may look like this. So here you notice, all these nodes N7, N4, N5, and these are modeling road intersections here. Just to show that correspondence a little bit easier, let me show you an overlay of these 2 images, and it may look like this. So you now see these nodes that we had in the graph, they match up with the road intersection. And then the edges we have, they match up with the road segments. Okay. So this is one way to model road maps in graphs, and it's a popular way to model that. Okay. It's often used for computing shortest path. Okay. Now when you look at this graph model and you try to compare with the entity relationship model we showed you in the last slide, you probably realize that this graph is not modeling all the information in that entity relationship diagram, right? So we can do a very quick big picture comparison of the 2 models and try to see the pros and cons. Okay. Before that, we'll also show you another example of graph model. If you remember the river network that we covered in the previous video, where you had these major rivers in United States, and we had a relationship called falls into. Okay, that may be modeled as a graph like this. So here river Mississippi maybe is node 1, river Missouri may be node, another node, and this arrow might show you that this large river falls into another river. Okay. So graph models can be used to model different spatial networks, but they are simple. Okay. So going back to the road example, and if you compare the entity relationship diagram for the roads and the graph model for the roads, here are the strengths and weaknesses of graph model. Okay. So in terms of strength, Graph models have very, very nice mathematics. In fact, there is a whole branch of mathematics called graph theory, which has characterized many properties of the graph, and it has classified graphs into different kinds. And those properties can help us reason about graphs very well. Okay? So for example, when we compute shortest path, this mathematics can help us tell whether the path returned by our algorithm is indeed the optimal or shortest path, or whether it is not. Okay? The second strength is that the graphs have been very popular in computer science, and over the last 50-60 years, computer scientists have designed very nice algorithms to manipulate graph. So you have enjoyed the fruits of those. For example, when you go to Google Map and compute shortest path, you probably do not realize how big a graph it is using to model roadmap of US. Okay, that graph has billions of nodes, and yet the shortest path is computed almost instantaneously. You don't even feel the time it takes, right? So those are the nice computational algorithms that have been designed over the last 50-60 years, and we can leverage those if we use graphs as the model. Okay? But what's the downside? Okay? And here is the downside. If you think about that entity relationship diagram I showed you, then graphs are modeling only a small part of that. Okay? And to be more precise, they are modeling only one binary relationship. Okay? So if you think of nodes as road intersections, then this relationship could be that a road segment connects to adjacent road intersection. Okay? But if you wanted to model another relationship, okay, besides connect, if you want to model, let's say, turn restriction, then there is a quandary. Okay? In a graph, you can only model one relationship well. Okay? So trying to model two relationships adds complexity, and I will illustrate that very quickly. And in fact, in many traditional graph theory and graph algorithms course, asking for a shortest path which minimizes turns or has no left turn often confounds these computer scientists, because that's a limitation of graph. Okay? Another implication of this is the following. Based on your preference for the relationship, right? In other words, if you look at your dominant queries, and those queries are asking for a different set of relationship than the one modeled by popular graph model, then you have limitations. Either you have to change your graph model or look for multiple graph model for the same road network. Okay? So let's look at an example of both. So let's first think about turn modeling, and we all know modeling turns are important in road maps. In fact, you might have even seen a recent New York Times story that a major logistics company, UPS, they were looking for new ways to minimize fuel consumption, going beyond what Google Maps can do for you. And one of the insights they had was that their trucks were spending a lot of time idling on left turns in the United States. Okay? If you were in Britain, and it may be the right turns, but usually the turns are asymmetric. One turn usually is quicker because you don't have to wait, and the other turn you have to wait for the opposite traffic to stop for you. Okay? And UPS noticed that, and they redid their routes to reduce left turns in the United States, and it saved them millions of gallons of fuel. Okay? So modeling turns are important societally. If you imagine everybody else doing that, you could probably reduce fuel consumption in a much bigger way. Okay? But how do we model that? Okay? So if you want to model that, there are a couple of different approaches. Okay? One approach is to translate it back to the basic relationship connects. And some people have tried that, but it simply expands your graph a lot. So let me illustrate that. So if you remember, this road map, so you have many one-ways here. So for example, if you think about this road intersection between this one-way and a two-way, then there are turn restrictions. For example, going this up like this, we cannot turn right, because it's a one-way. So if you want to model that, so then what we can do is to take the intersection N5 modeling this place and expand it further. Okay, expand it further into a bigger graph. Okay, and in that graph, you will have many extra edges modeling all possible turns. Okay, so in this graph, if you, let's say you are going on this one way, it is going up here, then this will allow you to turn in different direction. You can take a right turn, and you can take a left turn. Okay. However, if I was going on this road, okay, if I'm going on this road, which are these two edges, then I have a right turn available, but there is no left turn. I cannot go back this way. So that edge is missing. Okay. So this is one way to model the turns, and in this case your set of nodes and edges grow a lot. So essentially this node N5 now has been replaced by 6 different nodes and a bunch of edges. Okay? So if you were to do that, your graph size will go up. In addition, doing this is still, for no U-turn is harder, okay? Because U-turn involves actually a sequence of more than 2 edges, it's 3 edges. So it's a little harder here, okay? So there are some other approaches as well. Ideally we should switch to another notion called hypergraph and hyper edges. If you want to model U-turns, you may have to model 3 edges and so on, and that is very hard to model in regular graphs, but hyper edges and hypergraphs can do that. Another approach is to actually go beyond graphs. So whether you use graph or hypergraph, we can actually annotate. We can add some additional information to nodes like N5, a whole table which lists all possible turns, their delays and restrictions. And this is something commercial systems like ESRI have been, have gone this way. Okay? But again, the main point is that modeling multiple relationships is difficult, and we illustrated that by showing you the example of turn. Okay? Now another implication is that if you take a single spatial road, spatial network such as road map, then it has many different relationships, and depending on your workload or your application, the priorities of those relationships may be different. Okay? So depending on your favorite relationship, the graph model will also change. Okay? So for the same road map, you may see many different graph models, and we are going to show you a couple of those. The first one is the traditional one, okay, where the nodes represented road intersections and the edges represented these road segments connecting adjacent road intersection. Okay? This is a very popular one, and if you need to learn only one graph model for road maps, this is the one I will recommend. Okay? But we did see another choice. If you were to model turns, okay, if you were really interested in modeling turns, you were working for UPS, and that's what your application was, to minimize left turns, then what we could do is to use edges to model turn relationships. But then your nodes may switch from road intersections to road segments, because turns are relationships between road segments which are adjacent. Okay? Of course, you can have a third one, and this model will remind you of the model we used for the river network. We could use actually other types of nodes. So for example, the entire streets and avenues may be thought of as roads, and the relationship may be the intersects. Okay? Now this kind of a model is sometimes used for cartographic generalizations of road maps. Okay? So if you have a very large city, with many roads, and then you have to zoom out and you have to only show a subset of the roads, otherwise your picture may be cluttered. So in order to identify the major roads which should be shown, this third representation may be of interest, because you often prefer the roads which cover many other smaller streets, which they intersect with. Okay? So again, to summarize, what we looked at were conceptual and information models for road maps. And we saw that at a detailed information level called entity relationship diagram, where we can represent many concepts in roads, such as streets, road intersections, road segments, turns, etc. Then we looked at graph models, which are a nice clean mathematical model and also have been used in computer science to design many scalable algorithms. And we looked at the pros and cons of graph models. So even though it has very nice mathematical and computational properties, it has limitations. It can only model one relationship, and you have to choose which one. Okay? And based on your application, if you are doing cartographic generalization, you may choose nodes and edges in one way. If you are doing shortest path, you may choose them in a different way. Okay? So with this, we'll wrap up the discussion of conceptual models of street networks. When we come back in the next segment, we will look at logical models and look at query languages for spatial networks. And then we'll follow it up with another video on the physical model, the data structures and algorithms of spatial network. So look forward to seeing you in the next few videos. Thank you.